Okay, so picking up from where we left over from my previous recording, here we're continuing to do the derivation for the quantized energy level using the Bohr model. Okay, so getting started. We already have our equation 4, equation 11, and equation 7 written down. And let's just do the derivation together. So energy equals to 1/2 MeV squared minus the potential term VE squared 4 pi epsilon naught R. And in this case, we need to plug in our R into both this position and also into our velocity term. And we need to plug in our velocity term into here. So write it out. Let me just put in the velocity first. We have 1/2 ME times NH 4 pi MER minus VE squared 4 pi epsilon naught R. And here we can just cancel out our ME. That gives you NH over 8 pi ME oh sorry, I need to have the square here. 4 pi square, 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 that ends to be 1. So this ends up to be 8 pi square ME. On the top we have N squared H squared 1 over R squared minus VE squared 4 pi epsilon naught over 1 over R. And here we have R equals to R squared H squared epsilon naught. Just going to put it here for your reference. This is the equation we're using. You can plug in the terms. N squared H squared 8 pi squared ME. Here we have V squared e to the 4th pi squared ME squared N to the 4th H to the 4th epsilon naught square minus VE squared 4 pi epsilon naught. And we have VE squared pi ME N squared H squared epsilon naught R. And now we're ready to cancel some terms. N squared cancels out with N to the 4th. H squared cancels out with H to the 4th. Pi squared cancels out. One of the ME cancels out. And on the left hand side, that's it. On the right hand side, we have the pi cancel out. And I think that's it. And we can clear out the terms. On the left hand side, we have V squared E squared ME e to the 4th, I'm sorry. On the bottom, we have 8 N squared H squared epsilon naught square. Minus, on the right hand side, we have Z squared e to the 4th ME 4 N squared H squared epsilon naught. Or we can write that as negative 1 over 8 times V squared N squared times e to the 4th ME H squared epsilon naught squared. And again, for simplification, we can combine these constant term to a Rydberg, which is a unit for energy. So 1 Rydberg equals to e to the fourth me over 8 h squared epsilon naught squared. That's roughly 2.18 times 10 to the negative 18 joule. And the simplified energy equation now becomes En equals to negative V squared N squared, right? So the negative V squared over N squared times Rydberg, where N equals to 1, 2, 3, and etc. Right, so this is the atomic energy levels. For 1 electron atoms and cations. Well, I shouldn't say atoms because it's only hydrogen. So as a summary, what we have done here is we went over the derivation together, and here are the physical means of the Bohr model. Right, so only certain discrete orbitals are allowed in the Bohr model. And these atomic orbitals that are allowed are characterized by two properties. One, the atomic radii, or R, is quantized. Here we have Rn equals to n squared over z times the Bohr radii A naught. Second, the energy levels are quantized. So here also we derived the quantized energy level in the Bohr model. We have En equals to negative z squared over n squared. Here we're condensing all the constant terms into a new unit called Rydberg, where Rydberg is roughly 2.18 times 10 to the negative 18 joule. All right. So now we have the mathematical equation. How are we going to use our Bohr model? The first and most obvious application of the Bohr model is to interpret the atomic spectrum. All right, so remember when we talk about atomic spectrum, light of frequency mu is emitted or absorbed. So this delta E equals to h mu, or energy of the photon equals to h mu. So with equation 12, this is the energy equation we just derived. We have En equals to negative z squared over n squared times Rydberg, and n equals to 1, 2, 3, etc. What that means is we can predict the frequency of the light that's being emitted or being absorbed in the atomic spectrum. Just a quick note, the Bohr model works great for 1 electron atom, like hydrogen atom, or any 1 electron cations. So we're looking at the atomic spectrum, depending on where we're just using the emission spectrum, for example. Depending on where your energy level ends, we have different names for the series. Say if we end up, if the electron ends up in ground state, that's our Lyman series. If the energy ends up in my first excited state, or n equals to 2, that's our Balmer series, and that's in the visible region. Likewise, you have Paston series or bracket series, depending on where that end energy level is. And what it means in the emission spectrum, let's imagine we start from n equals to infinity, and depending on where it ends, you have different series. And we can use the Bohr model to calculate the frequency of the light that we expected to emit in the atomic spectrum. We'll see an example very soon, but let me just go over some of the other applications of the Bohr model. Using the Bohr model, we can also predict the ionization energy, or in this case, ionization energy is the minimum energy required to completely remove an electron from an atom. So if you think about it, is say we have start from a hydrogen atom in gas phase. We want to completely remove its electron to become AH plus. And if we look at the energy diagram, what it means by completely remove, we're talking about the electron originally stays in equals to 1 ground state. And it's completely removed means my energy level is positive infinity. And this delta E equals my ionization energy. And at n equals to infinity, we have En equals to 0. Okay. And let's do the quick calculation here for hydrogen atom ionization energy. We have ionization energy equals to Z 0, which is at n equals to infinity, minus the ground state energy, which we can use the Bohr model, and we can write it as 1 per atom. Right, so the ionization energy required to remove 1 electron from 1 hydrogen atom is 1 Rydberg. And we can do that calculation, translate that 1 Rydberg per atom into joule per mole. That's 1.31 times 10 to the 6 joule per mole. And you can check the experiment and see that actually matches up. And then we have some example questions here. This is one of the typical example questions you should expect on an exam. For example, considering Bohr model for a helium plus, where one of the things to keep in mind is now we're talking about helium plus, so Z equals to 2. That's a commonplace. People make mistakes. You could be asked to calculate the atomic radii of the n equals to 3 orbits. And remember, in this case, we're talking about the radii, right? So you need to know what is the correct equation to use, which in this case is Rn equals to n squared over Z times A naught. And here we know n equals to 3, we know Z equals to 2, and you can do the calculation. Likewise, you could be asked to calculate the energy, frequency, and wavelength of a photon that's emitted when the electron transmits from n equals to 5 to n equals to 2. So I'm just going to quickly show you how to set up the calculation. You can try it yourself, and the answer can be found in our annotated notes. So say this is my energy diagram. By reading the question, we know that the initial state is n equals to 5. And the final state n equals to 2. And we're talking about the transformation here, right? So that E photon equals to E initial minus E final. And we know in this case, we have the energy equals to negative V squared over N squared Rydberg. And you can just plug in numbers. We know what the Z is, we know what the N is. And that's the energy level. And by translating energy into frequency and wavelengths, we have E photon equals to H mu. Now you have our frequency. And we also have speed of light equals to frequency times wavelengths. And we have our wavelengths. So try it yourself, plug in the data, and compare it with the answer key and see how you perform in this question.